Hohmann transfer is a common orbital maneuver used by astrophysicists to send a spacecraft from a small circular orbit to a larger one. The maneuver is named after Walter Hohmann, who was a German scientist who first published a description of this type of maneuver in 1925. So when your Mars exploration spacecraft is in orbit around the Earth, it's also orbiting the Sun at the same rate as the Earth. For the purpose of a Hohmann transfer, this orbit around the Sun is the smaller circular orbit because the Earth is only 1 astronomical unit away from the Sun, while the average distance from Mars to the Sun is 1.52 astronomical units. In general, a Hohmann transfer orbit is the most fuel-efficient method of traveling between 2 planets. And so it's commonly used because using this approach, you can transfer the maximum amount of mission payload for a given amount of fuel. Because the Hohmann transfer is so fuel efficient, it is a fairly slow process. And so there may be advantages to other orbital transfers, but they will have other trade-offs, such as reducing the amount of payload that you can carry or requiring more fuel. So this diagram shows a Hohmann transfer that will bring a spacecraft from a lower circular orbit around the Earth into a higher circular orbit around Mars. The Hohmann transfer is an elliptical orbit, shown here in blue, with the Sun as one of the focus points. The ellipse touches both Earth's circular orbit around the Sun and Mars' circular orbit around the Sun. Launch occurs when Earth is at the Hohmann perihelion. That's the point of the Hohmann orbit that is closest to the Sun. And the spacecraft will arrive at Mars when Mars is at the Hohmann aphelion. That's the point of the Hohmann orbit that is furthest from the Sun. The spacecraft is going to travel 1/2 of this elliptical orbit as it travels from orbit around Earth to orbit around Mars. And so that's why this blue marking is only showing half of this ellipse. Okay. To make sure that the spacecraft and Mars arrive at the same place at the same time, the spacecraft has to be launched within a particular window of time. That window is called the launch window. If the spacecraft arrives too early or too late, it will arrive in Mars orbit, but it'll arrive at a time when the planet is not there. So that's the purpose of Part C, steps 1A through 1E. We are going to calculate some information which will help find the launch window. The first step, 1A, is to find the semi-major axis of the Hohmann elliptical orbit. The semi-major axis is 1/2 of the widest width of the ellipse. And you can see in this drawing dimensions of the distance of Earth from the Sun and Mars from the Sun that you can add together to get the full major axis. A is 1/2 of that amount. You can work in astronomical units, AUs. There is no need to convert to meters. In step 1B, we need to find the X and Y coordinates of the Sun. The Sun lies on the x-axis to the right of the center of the ellipse, as shown in this figure. So the y coordinate of the Sun is 0 because it's on the x-axis. The x coordinate equals the distance from the center to 1 focus point. And again, you can leave the units in AUs. There's no need to convert to meters. In step 1C, you need to define 3 parameters for the ellipse. The semi-major axis, which is called A, is the value you found in step 1A. So you've already found that. The distance from the center of the ellipse to one of the focus points is called C. by the way, in our previous notes, we have called this distance d, but you have found this value in the previous step. That was the distance from the center to the sun. So the final parameter that you need to find is called b. It is half the length of the minor axis of the ellipse, and you can find it from the following equation: b squared equals a squared minus c squared. In step 1e, you find out what position Mars is in when the spacecraft launches out of its Earth orbit. So Mars completes one revolution around the Sun every 687 days. In other words, Mars moves 360 angular degrees every 687 days. So first, calculate how many degrees does Mars move around the Sun in one day. Then we want to figure out how many degrees does Mars move during the Hohmann transfer. So take the travel time that you found in step 1d and multiply that by the degrees per day that Mars moves. That tells you how many degrees Mars moves during the Hohmann transfer. What we really want to find out is the initial angular position of Mars when the spacecraft begins its travel. So we know that the spacecraft needs to arrive at Mars when Mars has an angular position of 180 degrees. You can see that in this figure. So if you will subtract the angular motion of Mars from 180 degrees, you will get the initial position of Mars.